Welcome back. We just saw derivative for the exponential function. Derivative at any x is the function again times derivative at 0. Okay, so recall the function is exponential. So derivative at x is b to the power x f prime 0. In particular, we saw what happens when b was 2. When b is 2, derivative at 0 is approximately 0.69. When b is 3, derivative at 0 is approximately 1.10. Okay, so derivative of exponential function base 2 is 0 approximately 0.69 times 2 power x. Likewise, derivative of the 3 power x function is approximately 1.103 power x. So notice these two are strange numbers, right? So between 2 and 3, there should be a real number whose derivative at 0 is precisely 1 between these two numbers. Alright, so that number is the Euler number. Okay, Euler number or a Euler number. Okay, either way. So definition, the Euler number E is that real number such that limit h approaching 0, e power h minus 1 over h is 1. This, by the way, is the derivative of the exponential base e at 0. So, that's what derivative at 0 is 1. That's what we require. So, that number whose exponential function has derivative 1 at 0, that number is called the Euler number E. Euler number E is between 2 and 3 because 2 gives you something like this, 3 gives you something like this. So E will give you somewhere in between lies E whose derivative at 0 is 1. So this function fx equals e power x is called the natural exponential function. Derivative of f at 0 is 1. That's by design. That's how you found the number e. So this gives us an important result. Derivative of the natural exponential function is derivative is itself. Because all we were going to do is multiply by the derivative at 0. But derivative at 0 is 1. So I have to multiply by 1. So derivative of e power x is e power x. Alright. Which brings us to a beautiful example. Find the derivative of e power secant x. Well, this is fantastic because you know chain rule. Let u be secant x. Then e power secant x is e power u. So derivative e power secant x with respect to x is d by du of e power u du dx. So this was the chain rule. Derivative of e power u is e power u. Derivative of u being secant x, is secant x tan x. Replace the u back by secant x. So derivative of e power secant x is secant x tan x e power secant x. Alright. This is the graph of e power x. That's how it looks like. It's an increasing function with the y-intercept 0, 1. Because e is greater than 1, you see e is in fact between 2 and 3. So it's going to be an increasing function. So properties of the natural exponential function. The exponential function fx is e to the x is an increasing continuous function. Domain, the set of real numbers, and range 0 to infinity, open 0 to infinity. E power x is greater than 0 for all x in R. What happens when x approaches negative infinity? So you are taking left hand limit. Limit x approaching negative infinity of e power x is 0. Whereas on the right hand side, limit x approaching infinity of e power x is positive infinity. That is the x-axis The line y equals 0 is the horizontal asymptote for the curve y equals e power x. All right. The function fx equals e power x is one-to-one injective function. Notice it passes the horizontal line test. Okay. This can be seen by the fact that the graph y equals e power x passes the horizontal line test. Further, from the graph, we see that the range of f is 0 to infinity, which we already know, and domain is set of all real numbers. Now, here is a beautiful example to find the limits. Limit x approaching infinity, e power x over 1 minus e power x. What do we do? Well, e power x is a high power. It's an exponential function. Divide numerator and denominator by e power x. So numerator fetches me 1. Denominator fetches me, notice I have to distribute the division. 1 over e power x is e power negative x minus this fetches me 1. Now when I take limit x approaching infinity, this is e power negative x, right? E power positive x is here. So e power negative x will be like this, right? Decreasing function. So limit x approaching infinity of this guy is 0. So 1 over negative 1 is negative 1. Okay. Next, we have a very long problem. Let's work on it in our next video.